Look at your hands. They seem solid, don't they? They seem separate from the world around them. There's a place where you end and the air begins. There's a distance between you and the chair you're sitting in, between you and the screen you are watching, between you and the stars. This is the first and most fundamental truth of your experience. Separation, distance, the idea that you are here and everything else is over there, is the foundational assumption upon which you have built your entire life. Your sense of self, your understanding of the world. And it is a lie, a beautiful, persistent, and utterly convincing illusion. The universe has a secret it has kept for billions of years, written into the very fabric of existence, waiting for a mind curious enough to ask the right, impossible question. It is not a secret hidden in the dark voids between galaxies, but right here, inside of you. It is a ghost in the machine of reality, a whisper that connects everything to everything else, instantly, intimately, and irrevocably. It has a name that sounds more like a magical spell than a principle of physics. Entanglement. To understand it is to have the floor of reality fall away from beneath your feet. To truly grasp its meaning is to realize that the universe is not a collection of things, but a single, unbroken thought. And you're a part of that thought. So ask yourself, what if the distance between two particles, two people, two galaxies is just a stubborn illusion? What if, in a way your senses can never tell you, you're touching everything in the cosmos right now? This is not a story about science. It is a story about the nature of what is real. And it begins by dismantling the world you think you know. You believe in objects. You see a cup, a tree, a planet. You give them names. You treat them as distinct entities, self-contained and sovereign within their own borders. Your senses scream this truth at you every moment of your waking life. The solidity of the ground, the weight of a stone in your hand, the clear space between your body and another. This conviction, this belief in separation, is the bedrock of classical thought. It is the logic of Isaac Newton, a universe of elegant, predictable billiard balls, each following its own trajectory, influencing others only through direct contact or the steady, measurable pull of gravity over time. An action here causes a reaction there, but only after a signal, a wave, a force has had time to travel across the gap. Nothing can happen instantly at a distance. This is the rule of locality. It is the ultimate speed limit of the cosmos, the speed of light. It feels like common sense. It feels like truth. But the universe does not care for your common sense. Go deeper. Your senses are liars, but they're convincing liars. Let us peel back the first layer of their deception. The chair you sit on feels solid, immovable, but it is not. It is an illusion of solidity born from the frantic dance of countless atoms. And what are those atoms? They're almost entirely empty space. A tiny, impossibly dense nucleus, and a cloud of electrons orbiting in a vast, lonely void. If the nucleus were the size of a marble, the nearest electron would be a speck of dust a kilometer away. The solidity you feel is not a property of substance. It is the fierce protest of electromagnetic fields. The electrons in your hand repelling the electrons in the chair. You are not touching the chair. You are hovering an infinitesimal distance above it, held aloft by a force. The world is not made of things. It is made of forces. It is a universe of relationships, not objects. This is the first crack in the facade. The first hint that what you perceive is a convenient shorthand, a summary of a far stranger and more ephemeral reality. But this is still a local world. The forces act between neighbors. The electrons in your hand are repelling the electrons just next to them. The rule of locality still holds. The great lie of separation remains intact. To find the deeper truth, we must go deeper still, past the atom, into the realm where the very concepts of place and thing begin to dissolve into a mist of pure potential. We must go to the quantum realm. And here, in this shimmering, uncertain world, we find a connection that breaks the most fundamental rule of our perceived reality. a connection that seems to mock the vastness of space and the unyielding march of time. An instantaneous, unmediated, and perfect correlation between two particles, no matter how far apart they are. One particle on Earth, its twin in the Andromeda Galaxy, 2.5 million light-years away. If you ask a question of the particle here, its twin, across that unimaginable abyss, knows the answer instantly. Not in 2.5 million years. Not in a microsecond. Instantly. How? How can a whisper here become a shout there, without a voice to carry it across the void? This question would ignite one of the greatest intellectual battles of the 20th century. It would pit friend against friend, titan against titan. It would force us to choose between two pillars of our understanding. The comfortable, logical, local reality we thought we knew, and a new, strange, and deeply interconnected cosmos that the mathematics insisted was true. This is the story of that choice. A choice that began not with an experiment, but with a rebellion. A rebellion led by the most famous scientific mind in history, who, in trying to prove the universe was sane, accidentally uncovered its deepest and most beautiful madness. The year was 1927. The world of physics was in a state of beautiful, glorious chaos. The old clockwork universe of Newton was being dismantled piece by piece. A new generation of pioneers, young, bold, and unafraid of paradox, were sketching the blueprints for a new reality. Max Planck had revealed that energy was not a smooth, continuous flow, but came in discrete packets, or quanta. Werner Heisenberg had shown that there was a fundamental limit to what we could know, that the act of measuring a particle's position changed its momentum, and vice versa. This was his uncertainty principle, a declaration that at its most fundamental level, the universe was not a thing to be known, but a probability to be calculated. At the heart of this revolution was a Danish physicist named Niels Bohr. He was the poet-scientist, the philosophical visionary. For Bohr and his followers, this uncertainty was not a flaw in their theories or a limitation of their instruments. It was the truth. Reality itself, at the subatomic level, was intrinsically fuzzy, a shimmering haze of possibilities. A particle, until measured, was not in any one place. It was a cloud of potential, a wave of probability, existing in all its possible states at once. This was the principle of superposition. The act of measurement, the act of looking, was what forced the universe to make a choice. The wave of potential collapsed into a single, definite reality. A particle appeared here, not there. It spun up, not down. But before the measurement, according to Bohr, it was meaningless to even ask where it was or how it spun. The question itself assumed a reality that did not exist. This collection of ideas became known as the Copenhagen interpretation, and it was the orthodox view of the new quantum mechanics. But there was a giant in the room who refused to accept it. Albert Einstein, the man who had reshaped our understanding of gravity, space, and time. He was now the grand old man of physics, the skeptic, the conservative rebel. While he had been a key architect of the early quantum revolution, he could not stomach its final implications. God, he famously wrote to a colleague, does not play dice. For Einstein, the universe could not be a cosmic casino. The uncertainty and probability of Bohr's quantum mechanics felt like a surrender, an admission of ignorance disguised as a principle of nature. He believed in an objective reality, one that existed independent of our observation. A particle had to be somewhere, even if we did not know where. The moon, he argued, is still there even when no one is looking at it. He was convinced that quantum mechanics was simply an incomplete theory. There had to be something deeper, some hidden information, some hidden variables that determined the outcome of any measurement, if only we were clever enough to find them. The debate between Bohr and Einstein was more than a scientific disagreement. It was a clash of worldviews. Was the universe, at its heart, deterministic and knowable, as Einstein believed? Or was it fundamentally probabilistic and mysterious, as Bohr contended? For years, they argued through a series of brilliant thought experiments. Einstein would devise a clever scenario designed to expose a flaw or a paradox in quantum mechanics, and Bohr, after much thought, would always find a way to counter it, showing how the strangeness of the quantum world resolved the issue. Then, in 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, conceived of what they believed was the ultimate argument, the final, fatal blow to the Copenhagen interpretation. It was a thought experiment so clever, so profound, that it would echo through physics for the rest of the century and beyond. It would become known as the EPR paradox. It began, as all good quantum stories do, with a pair of particles. Imagine a system that decays into two new particles, flying off in opposite directions. The laws of physics, specifically the law of conservation of momentum, demand that their properties be linked. If you measure the momentum of one particle, you instantly know the momentum of the other, no matter how far apart they have become. They are correlated. Now, let's add the strange rules of quantum mechanics. According to Heisenberg's uncertainty principle, you cannot know both the position and the momentum of a particle with perfect accuracy. And according to Bohr's Copenhagen interpretation, these properties do not even exist until they are measured. Here was Einstein's masterstroke. Let the two correlated particles travel for a very, very long time, until they are light years apart. Now, make a measurement on particle A. You decide to measure its position. The moment you do, the wave function collapses, and it appears at a specific location. But wait, because of the uncertainty principle, by measuring its position, you have made its momentum completely uncertain. Now, consider particle B, light years away. You have not touched it. You have not interacted with it in any way. But because its momentum is perfectly correlated with particle A's, if you were to measure particle B's momentum, you would find it to be equally uncertain. This seems reasonable enough. But what if, instead, you had chosen to measure the momentum of particle A? You would get a definite value. And because of the correlation, you would instantly know the definite value of the momentum of particle B light years away. By measuring particle here, you have somehow given particle B a definite momentum over there. Here is the paradox. You, the experimenter, have a choice. You can measure the position of particle A, or you can measure its momentum. According to quantum mechanics, your choice here, now, seems to instantaneously affect the properties of particle B light years away. Either information is traveling faster than light, which Einstein's own theory of relativity forbade, or particle B somehow knew what measurement you were going to make all along. To Einstein, this was absurd. He called it spukhaft Fernwirkung, which translates to spooky action at a distance. He saw only two possible explanations. One was that the universe was indeed spooky, non-local, and that an action in one place could have an instantaneous effect in another. He rejected this out of hand. It violated the very fabric of space-time as he understood it. The other explanation, the one he championed, was that quantum mechanics was incomplete. The particles were not a haze of probability. They had definite properties from the moment they were created. They were like a pair of gloves, separated and put into two boxes. If you open one box and find a left-handed glove, you instantly know the other box contains a right-handed glove. There is no spooky action. The information was always there, hidden from you until you looked. These pre-existing properties were the hidden variables he had long suspected. The EPR paper was a direct challenge. Quantum mechanics, as it stood, could not be a complete description of reality. It presented a choice. Either accept spooky action at a distance, or admit that there's a deeper, more sensible reality hidden beneath the quantum fuzziness. For Einstein, the choice was obvious. Reality was local. Therefore, quantum mechanics was incomplete. He thought he had won. He thought he had exposed the madness at the heart of the new physics. Niels Bohr was reportedly stunned by the paper. He spent weeks pacing, thinking, refining his response. His counterargument was subtle and profound. He argued that Einstein was making a fundamental mistake in thinking of the two particles as separate entities. From a moment of their creation, he said, they were not two particles. They were a single, unified quantum system, described by a single wave function, no matter how far apart they traveled. To measure one was to measure the entire system. The question of how a signal traveled from one to the other was meaningless because there were not two separate others, there was only one it. For nearly 30 years, the debate remained purely philosophical. A battle of giants fought with thought experiments and interpretations. There was no way to test it. Was Einstein right, and reality was a sensible, local affair with hidden information? Or was Bohr right, and reality was a deeply strange, non-local, interconnected whole? Science had no answer. It was a matter of taste, of intuition. And then, in 1964, a quiet, thoughtful physicist at CERN named John Bell decided to take another look at Einstein's argument. He was sympathetic to Einstein's view. He, too, felt that there must be a more reasonable reality underneath it all. He wanted to formalize Einstein's idea of hidden variables and see if he could make it work. What he discovered changed everything. John Bell was not a showman like Bohr or a global icon like Einstein. He was a humble genius from Belfast who simply wanted to understand the truth. He translated the philosophical debate into the clear, unforgiving language of mathematics. He took Einstein's idea of local hidden variables, the gloves and the boxes, and worked out its logical, statistical consequences. He reasoned that if the particles had predetermined properties, like the handedness of the gloves, then the correlations between measurements on the two particles, when measured at different angles, could only be so strong. There is a mathematical limit, an inequality, that any local, common-sense theory had to obey. Then, he did the same for Bohr's quantum mechanics. He calculated the correlations that the standard theory predicted, and he found that they were different. Quantum mechanics predicted stronger correlations than any possible theory based on local hidden variables. The predictions of Bohr and Einstein were not just philosophically different. They were experimentally distinguishable. Bell had found a way to put reality itself on trial. He had turned a philosophical argument into a testable hypothesis. His work, now known as Bell's theorem, was a mathematical knife edge. On one side lay Einstein's universe, local, sensible, and intuitive. On the other side lay Bohr's, strange, probabilistic, and deeply, mysteriously connected. All that was needed was an experiment to ask the universe directly which side of the line it lived on. To understand the test, we must first understand the connection itself. What exactly is this strange marriage between two particles? It is a covenant, a vow of opposition. Imagine you have a machine that creates pairs of subatomic particles, let's say photons, and sends them flying in opposite directions. These photons have a property called polarization, which you can think of as the orientation of a light wave. We can measure this polarization with a filter like the lens of a pair of polarized sunglasses. If the photon's polarization matches the filter's orientation, it passes through. If it's perpendicular, it's blocked. Now, these entangled photons are created in a special state. They are created with opposite polarizations. But according to quantum mechanics, neither photon has a definite polarization before it is measured. Each is in a superposition of all possible polarizations. It is not horizontally polarized. It is not vertically polarized. It is a cloud of pure potential. What is certain is the relationship. If you measure one photon and find it to be vertically polarized, you know with absolute certainty that its twin, no matter how far away, will instantly take on a horizontal polarization. This, by itself, is not yet spooky. This is the part Einstein could accept. This is the glove analogy. Maybe one photon was born vertical and the other born horizontal. The information was hidden, but always there. The genius of Bell's test was to introduce a twist. Literally, what happens if you measure the two photons with filters set at different angles? Not just vertical or horizontal, but at, say, 30 degrees or 60 degrees. In Einstein's world of hidden information, the particles have definite polarizations all along. You can calculate the probabilities. If you and your friend across the galaxy have randomly oriented filters, you can work out how often you'd expect your results to match or mismatch based on classical statistics. There's a clear limit to the correlation. But in Bohr's quantum world, the particles have no pre-existing polarization. They are a single system. When you measure the first photon at a 30-degree angle, the entire two-particle system reconfigures itself. The outcome here is not independent of the angle of the measurement over there. The math of quantum mechanics predicts that the correlations will be stronger than Einstein's common sense limit allows. The gauntlet was thrown down. The experiment was designed. For a decade, the technology was not precise enough to perform the test conclusively. There were loopholes. Perhaps the detectors were inefficient. Perhaps the particles were somehow communicating, but slower than light. The results were tantalizing, always leaning towards Bohr, but never definitive. Then, in the early 1980s, a team in France led by a young physicist named Alain Aspect conducted a series of brilliant, elegant experiments. They created entangled photons and sent them down long fiber optic cables to two separate detectors. To close the communication loophole, they used ultra-fast switches that changed the orientation of the polarization filters after the photons had already left the source. The choice of measurement was made so quickly that there was no time for any signal, even one traveling at the speed of light, to pass between the particles and inform them of the setting. The experiment was a direct interrogation of reality. It asked a simple question: do you obey the common sense limit of Einstein or the strange predictions of Bohr? The data began to come in. The correlations were calculated, and they violated Bell's inequality. Conclusively, dramatically. Einstein was wrong. The universe is spooky. The results were a thunderclap in the world of physics. It was not a matter of interpretation anymore. It was an experimental fact. The world is not local. The hidden variables do not exist. The connection is real. Bohr's strange vision of an interconnected, probabilistic reality had triumphed. The shadows on the wall of the cave had spoken, and they told a tale of a reality far more unified than our senses could ever perceive. The evidence was not in seeing the connection, but in seeing its undeniable effects. It was in the fingerprints left in the statistics, the ripples on the pond of probability. Science had confirmed it. The foundational assumption of our experience, that of separation, is false. There is no here and there in the way we understand it. There's only a single, sprawling quantum state. This changes everything. It shatters our most cherished intuitions about how the world works. The concept of locality, the idea that an object is only directly influenced by its immediate surroundings, is not a fundamental law. It is an emergent property, a habit of the macroscopic world we live in. It is a useful fiction. But what is this connection? How do we wrap our minds around it? The phrase faster than light is often used, but it is deeply misleading. It is not that a signal travels from particle A to particle B. It is not communication in any classical sense. You cannot use entanglement to send a message. If you are the observer at particle A, you cannot force it to have a specific outcome. The result of your measurement is always random. You will find it is vertically polarized 50% of the time and horizontally polarized 50% of the time. You cannot control the outcome to send a Morse code of up and down to your friend across the galaxy. The magic is only apparent after the fact, when you and your friend meet up and compare your notebooks. You will find that every single time you measure vertical, your friend measured horizontal. Every time, a perfect anti-correlation. The randomness on your end was perfectly mirrored by the randomness on their end. So, it is not action at a distance. It is oneness at a distance. The two particles were never truly two. They are one entity, expressing itself in two different locations. Think of a single object, like a coin, that is somehow present in two places at once. When you look at it here and see heads, the tails that must exist to complete the coin is instantly manifest over there. It did not send a message to itself. It simply is itself. This violates our ingrained classical logic. We see two distinct phenomena in two distinct places and assume a cause and effect relationship that must unfold in time. We look for the messenger. But the universe insists there is no messenger because there is no message to be sent. The information was never separated. Only the manifestation was. This leads us to the deepest and most unsettling part of the entire quantum story, the role of the observer. The measurement problem. In the classical world, measurement is a passive act. You measure the length of a table. The table has a length, and your measurement simply reveals it. You are a spectator. But in the quantum world, you're not a spectator. You're a participant. Before your measurement, the entangled pair exists in a state of pure, indefinite potential. The first particle is not spinning up or down. It is in a superposition of both. The second particle is also in a superposition of both. They exist together in a single mathematical description that simply says whatever one is, the other is the opposite. The moment you choose to measure the spin of particle A, that entire cloud of possibility collapses. Reality is forced to make a choice. The particle you are observing randomly becomes up, and in that exact same instant, with no time delay, its twin, a universe away, becomes down. Your act of looking here did not just reveal a property. It created a property. And in doing so, it simultaneously created a property in a place you could not possibly have had time to influence. Think about what this means. Your conscious decision to perform a measurement, the physical act of your apparatus interacting with a particle, is an event that has instantaneous, non-local consequences. You are not a detached observer of the universe. You are inextricably woven into its functioning. Your observation is a creative act. You are a co-creator of reality. This idea is so profound, so challenging to our sense of self and our place in the cosmos, that physicists have spent decades trying to understand it, explain it, or explain it away. Some theories propose that the universe splits into multiple parallel worlds with every quantum measurement, one where the particle was up, another where it was down. Others suggest that the collapse of the wave function is not instantaneous, but just very, very fast. Still others propose that information is somehow conserved in ways we do not yet understand. But the simplest, most direct interpretation of the experiments remains the most radical. What we do here and now can shape what is real over there, right now. The fabric of reality is not a static stage on which events unfold. It is a dynamic, participatory web, and we are one of its threads. The implications of this ripple outwards from the subatomic to the cosmic, and ultimately into the very definition of what you are. If the fundamental constituents of the universe are not separate, independent things, then what are you? You're a collection of somewhere between 7 and 10 octillion atoms. Each of those atoms is a seething dance of quantum particles. These particles were forged in the hearts of long-dead stars, and they have been part of countless other systems before they came to be you. They are entangled, not just with each other, but with particles scattered across the cosmos. The electron in a carbon atom in your hand may have a quantum twin in a distant nebula, their fates still bound by a vow made billions of years ago. You are not a single, self-contained entity. You are a temporary, stable pattern in the universal quantum field. You are a standing wave of unbelievable complexity. You are a locus of cosmic entanglement. The feeling of being a solid, separate self is an emergent phenomenon, a high-level abstraction. It is a useful story your mind tells itself to navigate the macroscopic world. But at the fundamental level, you are not separate from the universe. You are the universe, experiencing itself as you. This forces us to ask an even more profound question. What does it even mean for something to be real? Our classical notion of realism is that things have definite properties that exist whether we're looking or not. The moon is still there. But entanglement proves this is not true at the quantum level. A particle does not have a definite spin until it is measured. Its reality is conditional, relational. It only becomes definite in its interaction with something else, in this case, an observer. So, is reality the property of an object? Or is reality the relationship between objects? The experiments suggest the latter. A thing is not defined by what it is in isolation, but by how it is connected. Its being is its entanglement. This is a radical shift in our ontology, our theory of existence. We are moving from a universe of nouns to a universe of verbs. Things are not the primary reality. Interactions, relationships, and processes are. An electron is not a thing. It is a set of potentials for interaction. You're not a thing. You are a symphony of interactions, a confluence of relationships that holds itself together for a brief, glorious moment. And what of space itself, that seemingly empty canvas on which reality is painted? Entanglement suggests that space might not be fundamental. Perhaps the reason two entangled particles can influence each other instantly across vast distances is that, at some deeper level, they're not distant at all. They are adjacent. Some physicists now speculate that space-time itself is not the foundation of reality, but an emergent property of a deeper layer of quantum information. They imagine that the universe is built from countless qubits of entangled information, and the geometry of space and time is a manifestation of the pattern of their entanglement. In this view, entanglement doesn't happen in space. Entanglement creates space. The more entangled two bits of information are, the closer they are in the emergent geometry of space-time. This is the ER equals EPR conjecture, a fascinating and speculative idea that links entanglement, EPR, with wormholes or Einstein-Rosen bridges, R, in space-time. It suggests that every entangled pair is connected by a microscopic wormhole. The universe, then, is not a vast, empty space with a few things in it. It is a dense, interconnected network, a cosmic switchboard, where every point is fundamentally connected to every other. This line of inquiry inevitably leads us to the greatest mystery of all, consciousness. Is it just a coincidence that the strangeness of the quantum world seems to hinge on the act of measurement or observation? Is it just a coincidence that reality seems to wait in a state of potential until a conscious or quasi-conscious agent interacts with it? This is, for now, the realm of speculation. It is a dangerous and beautiful frontier where physics meets philosophy. There is no proof, but the questions are too compelling to ignore. Could consciousness be a macroscopic quantum phenomenon? The human brain is a warm, wet, and complex environment, long thought to be too chaotic for delicate quantum effects like entanglement to survive. But recent discoveries in quantum biology are challenging that assumption. Photosynthesis, the sense of smell, the navigation of birds, all of these seem to rely on quantum mechanics to function. Nature, it seems, learned to harness the quantum world long before we did. What if the brain has done the same? What if the neural network that produces your thoughts, your feelings, your sense of self is somehow stabilized or enhanced by quantum entanglement between molecules or electrons within your neurons? What if your unified, single experience of consciousness, the feeling that you are one I and not a trillion separate cells, is a reflection of the underlying quantum coherence of your brain? In this view, consciousness is not an emergent property of classical computation, like software running on the hardware of the brain. It is a fundamental property of a universe that the brain has evolved to harness and amplify. It is the ultimate observer. Your personal experience of collapsing the wave function is not just a metaphor. It is what you are doing every single moment. You are the universe's way of choosing one path out of an infinite sea of possibilities. Perhaps the universe is not just a physical system. Perhaps it is a participatory system that only becomes fully real when it is observed. The physicist John Archibald Wheeler called it the participatory universe. He suggested that the universe, through us, is observing itself, and in doing so, bringing itself into being. The past itself, he argued, is not fixed until it is observed. An observation made today on a photon from a distant quasar could, in principle, affect the path that photon took billions of years ago. This is the ultimate loop of causality. We are born from the universe, and the universe is born from our observation of it. We are not strangers looking in from the outside. We are the cosmos looking at itself. So, we return to where we began. We return to Einstein's ghost, his spooky action at a distance. After this long journey through paradox and philosophy, we can now see it with new eyes. It was never action, because no force was transmitted. It was never truly at a distance, because the particles were never truly separate. The spookiness was not in the universe. It was in our assumption of separation. We were the ones haunting reality with our limited intuition. The great lesson of entanglement is not that the universe is strange. It is that the universe is whole. It is a single, indivisible entity. Its apparent divisions into galaxies, stars, planets, and people are a matter of perspective, not fundamental truth. There's a powerful metaphor that might help us grasp this. Think of a hologram. If you take a holographic plate and shine a laser through it, it projects a three-dimensional image. But the magic of a hologram is that if you break the plate into pieces, each piece, no matter how small, still contains the entire image. The whole is encoded in every part. Perhaps the universe is like this. Perhaps you are not just a piece of the universe. Perhaps you contain the whole. The laws, the history, the potential of the entire cosmos are encoded within you, within every particle that makes you up. Your entanglement is your connection to this wholeness. What does this mean for you in your life? It means that the feeling of isolation is an illusion. The sense of being a skin-encapsulated ego, separate and alone in a vast, indifferent cosmos, is a profound misunderstanding of your nature. You are connected. Your very substance is woven from the same thread as the most distant star. The boundary between you and the world is porous. It is a convention, not a reality. The questions that entanglement raises are not just for physicists. They are for every one of us. What is a relationship, if not a macroscopic form of entanglement? What is empathy, if not the intuitive recognition of this shared, underlying reality? What is love, if not the experience of collapsing the boundary between two parts of a single whole? We have not solved the mystery of entanglement. In a way, we have only deepened it. We have confirmed its existence. We have begun to harness it for new technologies like quantum computing and secure communication, but its true meaning still lies just beyond our grasp. It is a question the universe is asking about itself, and we are the instruments through which the question is being explored. So, look at your hand again. They're not just solid matter. They're a trillion quantum events, a chorus of probabilities collapsing into a momentary form. They are woven from stardust and held together by the memory of a cosmic vow. They are entangled with the beginning of time and the edge of space. You're not a stranger here. You're a feature of the cosmos, not a bug. Your consciousness is not an accidental byproduct of chemistry. It may be the very thing that lights up the world. The journey into the heart of matter has not led us to a final, simple building block. It has led us to a mirror. It has led us back to ourselves and to our intimate, unbreakable, and truly mysterious connection with everything that is, was, or ever will be. You're not a drop in the ocean. You're the entire ocean in a single drop. And the name for that ocean is reality.